Hello everyone, I'd like to welcome you all to this presentation on how Canada is contributing to the International Height Reference Frame, which is through regional geoid modeling and modernizing its height system. My name is Ismael Foroughi and I work with Natural Resources Canada. I will start by introducing Canadian Geodetic Survey and its role in the Natural Resources Canada. And we'll go over Canadian Spatial Reference System and talk in detail about how this system is modernized in two dimensions, the geometric side and also the height side. We will briefly talk about the parameters of the International Height Reference System and how it's realized in form of IHRF. And what is the role of Canada? What does Canada contribute to the IHRF? And in detail, we will see the large project of the height system modernization in North America, which is a collaborative project between Canada, USA, and Mexico. The main mission of the Canadian Geodetic Survey, as one of the organizations of Government of Canada, is to provide fundamental reference values to measure coordinates and gravity everywhere in Canada. This will also cover monitoring the motions of our continental landmass, and it is there to support many geomatics and geoscience applications. In a simple word, CGS role is to define and provide access to coordinates, to tools, and all the products related to the reference systems. My talk today is mainly from the activities of the Gravity and Height System group. We are one of the 4 groups of the CGS, and we focus on heights and gravity across Canada. Indeed, we are in charge of maintaining, modernizing, and support of leveling network, gravity network, and geoid determination in general in Canada. The pictures you see to the right, these are the members of our small but very strong group. The geodetic foundation of all positioning and mapping activities in Canada, it is under the Canadian Spatial Reference System, or CSRS, and it tries to provide a consistent spatial framework for every application, from cadastral surveying to environmental monitoring, and etc. CSRS has 3 key pillars. The first one is the horizontal reference, which is based on North American datum of 1983 or NAD 83 CSRS. It's a reference frame that also incorporates the tectonic motion, and it's realized through a network of continuously operating GNSS stations. And Canada right now is working with US to modernize the system into NATREF 2022, which is a continental effort to align the North American reference systems to the IHRF standards. The second one is the vertical reference, which is defined by the Canadian Geodetic Vertical Datum of 2013. It has a geoid model, which is its realization, and it helps to relate the GNSS-derived geodetic or ellipsoidal heights to the orthometric heights, which is the current official type of height used in Canada. Canada again is working with US through modernizing this realization, and I'll talk about it later in this presentation. The third pillar of CSRS is the Canadian Gravity Standardization Network, or CGSN, and that's a set of gravity stations, primary and secondary, some with absolute gravity values, some have been surveyed with relative gravimeters but have the absolute value. It provides a high accuracy gravity measurement across the country, and it's the main one to use for, let's say, geodynamic changes, and it's connected to the IHRF. The height systems could be defined internationally, which is called the International Height Reference System. This is a global concept that really defines height based on the Earth's gravity field. And that's a replacement of the sea level as the reference, which was traditionally used by a lot of countries, and the problem with them was that then there were always inconsistencies between the borders. IHRS, it uses an equipotential surface of the Earth, which is a surface that the potential is constant everywhere, or technically the water really doesn't flow from one point to the other point. It is based on a geoid, or it is based on a potential value that is fixed, W0. That W0 value was adopted in an IEG resolution back in 2015, and it is set to mean as the zero height across the world. So technically it's a zero height surface. And when we want to define the height of the point, what we do usually is that we measure the gravity potential of that particular point from this W0 value, and that difference is called then a geopotential number. It's a unique number to every point. IHRS is based on the mean tidal reference, and it has some constraints to connect to the physical properties of the Earth, and one of them is just that the potential of the points, they actually go to zero when you go away from the reference surface, and so that's kind of a consistent way to define height globally, and it's very critical surface for a lot of applications like sea level monitoring, because we want to do that globally really, and climate studies, etc. While IHRS is a system, is a concept, the International Height Reference Frame, that is an actual realization of this system. IHRF is a network of reference stations across the world where we can really measure heights in practice. Each IHRF point or station has a precise potential value, or WA, usually coming from GNSS coordinates in the IHRF system, and also coming from gravity observations. Some come from geoid modeling, which we'll go through later. And then there is a geopotential number, which is the difference between the W0 and the WA. Once we have the geopotential number, then we can actually compute physical heights. That really depends on different countries. Some go with normal height, some go with orthometric, some it's like normal orthometric, which is really a simple division of geopotential number by the average gravity along the plumb line from that point to the reference surface, or any other plumb. Like I said, I don't want to go through that. It's just a way of defining physical heights from geopotential number. And you see a diagram here to the right. That's how the physical heights are defined in Canada. That's the orthometric heights. So we measure the mean gravity along the plumb line for this part. Canada supports and contributes to the IHRS and IHRF initiatives. It proposed several IHRF stations, and these stations meet the criteria set by the IAG. Some of these criteria include, for example, a dense terrestrial gravity data around each station and the connectivity to the national leveling networks. You could see in the plot to the right some of these stations, and those points around each, they show the terrestrial gravity data just to ensure that we have an accurate gravity value at these stations. Like I said, CGS, or Canadian Geodetic Survey, as part of NRCan, is in charge of that, and it's the organization contributing to the IHRF. And what we do really is providing the terrestrial gravity value and also the potential value at these stations, which the potential value is derived from the Canadian regional geoid model, which I will talk about it later in this talk. The current height system in Canada is the Canadian Geodetic Vertical Datum of 2013, and its realization is a Canadian gravimetric geoid model of the same year. It is computed using Stokes-Helmert method, and it's the official system right now. You could see some of the parameters of such system in a table to the right, and I highlighted the W0 value, which is different than what was proposed in the IHRF, in the IHRS system. So that literally shows the inconsistency between different countries if they were to choose their own height system, and it shows the importance of the IHRS. Like I mentioned, Canada's contribution to IHRF stations is coming from the potential values derived from a geoid model. Right now, Canada is working with the US and also Mexico to modernize the height reference systems across the North America. US is moving into a new vertical datum, which is called North American Pacific Geopotential Datum, or NAP-GD 2022. It's a gravity-based height system, which is going to be new for the US, but it has been in place for Canada since 2015, which was called CGBD 2013. In Canada, we will keep the CGBD 2013 for now, but we're very closely involved with the development of a new shared geoid model, or a new realization. This geoid model it's a collaborative effort between Canada's CGS, US National Geodetic Survey, and also Mexico's NEGI. Together we developed a new common geoid model which covers a quarter of the Earth, and it's called Geoid 2022. And it's a common geoid model to be used between US and Canada, but I'm not 100% sure about the decision from Mexico. So the new contribution of Canada to IHRF will be coming from this new geoid model, and of course there are some differences between this one and the one that is officially in place right now. A little bit of background about this initiative, because I think it's important if any of the neighbor countries ever decide to have a common geoid. For us, between Canada, US, and Mexico, this was a truly continental collaboration. So we started sharing our data sets, which was like terrestrial data set around 2.1 million gravity observations. Of course, the quality and the spacing of such observations vary, specifically in the remote regions. We also used the GravD airborne gravity data, which was a national airborne gravity saver over the US. We used the Sattel altimetry derived gravity from DTU1, and for the topography corrections, we used a common DEM, which we call it DEM 2022. It was a combination of TandemX, American's national elevation data set, and also Merit DEM. And we also had, over the Greenland, we used the ice thickness data because that really helps to weather estimate the gravity signals beneath the ice. And at the end, we combine all of this data. The data was shared between all the three agencies, and it was used to compute different geoid models from each agency. Each agency used different techniques to compute the geoid. At CGS, we used the Stokes-Helmert. NGS used Molodensky approach. We compute geoid. NGS computes quasi-geoid, which is then converted to geoid. In the beginning, the two models were not really converging, so there were large differences, but we worked together on the topography corrections, on the data preparation side, etc. So the differences are now at the same centimeter to decimeter level. What you see in the plot here, these are the differences over the Great Lakes. So you could see the maximum is like around 15, plus minus 15 centimeter. Inegi's method is very close to CGS, so I did not include it here, but the CGS's geoid and Inegi's geoid are also very much aligned. This is a plot of the geoid 2022, which is computed by the arithmetic mean of the two geoid models computed by NGS and CGS. You could see the parameters are pretty much close to CGBD 2013, but now the geometric reference frame would be IHRF 2020, and with the reference epoch to 2020. The differences between the current geoid model and the upcoming geoid 2022 ranges up to decimeter level. The new geoid model has higher resolution, 1 minute compared to 2 minutes. It has DEM, EGM, satellite altimetry, airborne gravity data. There is a new error model for that, which also incorporates the DEM error into the error estimate. And essentially what you see here would be the differences at the IHRF stations, which will be in place when the new geoid model is adopted in Canada. Some final takeaway point is that Canada contributes to IHRF by providing potential values for selected reference stations using a regional geoid model. This model, which is CGG 2013A, computed by Stoics Helmet method, is maintained and updated by the Canadian Geodetic Survey whenever new data or methods are available. Looking ahead, Canada and the USA are moving towards a shared geoid model, which is Geoid 2022. Once this model is officially adopted, then the potential values of the IHRF points will be updated to reflect the new reference surface at the international level. Thank you very much for listening.